Hello everyone, welcome back. Let's do the next set of 5 questions, question number 6 to question number 10, organic question from June 2020 CSIR-NET question paper. Okay. So the question number 6, it says, the correct statement about the orientation of bromine atoms in the most stable conformation of A and B. So let's draw the stable conformation of both of them and then let us see. So of course both of them are cyclohexane, so the stable conformation is chair, and chair we know they will flip. So please understand, when we convert this planar structure into chair conformation, whichever substituent is towards the viewer, that we put above the plane, and whichever substituent is away from the viewer, that we put below the plane. Okay, so you are having A and you are having B. Let's solve it. So this is the one structure. So once we draw cyclohexane, you can see here this M is above the toward the viewer, so we draw it above the plane. On this carbon, randomly you can choose any carbon. I have chosen this carbon, and bromine is away from the viewer, so below the plane. So this is position number 1, position number 2, position number 3. So again 1, 2 and 3. So here methyl is towards the viewer, so above the plane, so it is coming in axial position. I hope everybody knows how to draw axial and equatorial. Okay, now when it flips, all the axial bond becomes equatorial and all the equatorial bond becomes axial. So now when it flips, this methyl goes in equatorial position. Please see, it was above the plane here. Here also it is above the plane, and Br is below the plane. But Me from axial it becomes equatorial, and bromine from equatorial becomes axial. Similarly here, methyl from axial becomes equatorial, and hydrogen from equatorial becomes axial. So of course this is more stable than this one, because here two bulky methyl are in equatorial, whereas here two bulky methyl groups are in axial. You know, substituents do not prefer axial position because of 1,3 diaxial interaction. First is these two will interact, and then one another hydrogen is here, this will also interact. It creates lot of steric hindrance. But whereas it comes in equatorial position, the problem is not there. So in first molecule A, Br will occupy axial position. Moving on to the next question. So again we draw one of the chair conformation, and Br is towards the viewer, so I am taking this as the starting one. So Br is above the plane here in axial position. Then 1, 2, 3, at position number 3, methyl is towards the viewer. So methyl, I should have drawn more straight. Okay, methyl comes in axial position here. Hydrogen is away from the below the plane, because it is away from the viewer. And similarly this methyl is away from the viewer, so it is here. So here all three are in axial position, definitely not stable conformation. It will flip, and when it flips, bromine from axial goes to equatorial, then methyl from axial goes equatorial, this methyl to equatorial. Thus here bromine will be in equatorial. So answer is option B. That means in molecule A, bromine is in axial position, and in molecule 2 bromine is in equatorial position. Going to the next question, the synthetic equivalent of the given synthon. Synthon, C double bond O, where it acts as both electrophile and nucleophile. So it's like when we talk about synthon, like what molecule which you use so that it will give this kind of species, okay, equivalent to this. So let's draw all of them: tetrabutyl isocyanate, tetrabutyl cyanate, tetrabutyl cyanate, and tetrabutyl isocyanate. So in retrosynthetic analysis, a synthon is hypothetical unit within a target molecule that represent potential targeting reagent in retroactive synthesis of the target molecule. So it is a hypothetical unit. This is what we want. So if you look at option A, tetrabutyl isocyanate, carbon has negative polarity, so this can go and attack here, right? And this leaves. And also if you take something like negative RMGX, so this can attack this carbon, and this on nitrogen you can see very clearly has positive charge, so this will go and attack here like that. So that means once you hydrolyze, all this will go off and you get back C double bond O. So you are having species where carbon has both positive and negative polarity. Thus the answer is option number A. Moving to the question number 8, the correct order of carbonyl stretching frequency for the given compound. So you are having this, it is asking. So one thing we know about IR, stretching frequency basically comes from the Hooke's formula. the frequency nu bar is directly proportional to K and inversely proportional to reduced mass. So here we are talking about K. K is force constant, how strong is the bond. Now here carbon is sp hybridized, you can see here, because it has two p orbitals, one p orbital like that and one p orbital like that, and one is forming pi bond with oxygen, another is forming pi bond with carbon. So when carbon is sp hybridized, it has more s character. So when it has more s character, that means s orbital is closer towards nucleus. Okay, so it is more electronegative. So when it is more electronegative, it will pull the bonds more strongly towards itself. So this bond becomes stronger and therefore stretching frequency is higher. So very clearly B will have highest. Now we have to compare between A and C. Now we have to compare between A and C. What happens in A and C? In A we have cyclopropane. Now cyclopropane is highly strained ring. See this angle, it is 60 degrees. What is the angle required? Angle is angle required for sp3 is 109, whereas bond angle required for sp2 is 120. That means sp2 is more uncomfortable than sp3 hybridized. So what it does, it this carbon carbon orbital, what happens is the bond inside the ring, they get more p character. So that because we saw sp3 is more comfortable than sp2, because sp3 is having 109 degrees whereas sp2 has having 120 degrees. So as p character increases, uh, bond angle requirement reduces. So what happens, this carbon, the inside bonds, these two bonds, they get more of p character. If you look at Jerry March, they call it almost sp5. At expense of this, they get more of s character here, but more of p character inside the ring. So when it is having more of s character here, it will pull the electrons more strongly than this one. Okay, because this is sp2. So first will be B, then A, then C. Thus answer is your option D. B is having highest, then A, then your C. Okay. What I have written here, please go through it slowly. I am going through slowly. You can pause it and you can read it again and again. Okay. Moving to the next question. The correct order of pKa for the following compound. Okay. pKa. pKa means it is inversely proportional to your Ka value, because pK is negative log of Ka. Now what is Ka? Ka is dissociation constant. How strong is the acidity, higher will have Ka value and smaller will be pK value. Now look here, if you remove proton from here, I would have done here. If you remove proton from here, you're getting this species. Now this is anti-aromatic because cyclic planar, but it follows 4n electrons. It does not follow 4n plus 2, anti-Huckel's rule. Okay, so it is anti-aromatic because 2 electrons in this pi bond, 2 electrons here, and all are conjugated next to each other. So each of them is having orbital. These both have 1 electron and this has 2 electron and they overlap. So this is not at all stable. So very difficult to remove this proton. So that means very low Ka value, that means very high pK value. Whereas this is very acidic because if you remove this proton, you get negative charge. Now what happens? 2 electrons here, 2 electrons here, and 2 electrons here, it becomes 6 electron. So it is following Huckel's rule, cyclic, conjugated, planar, and having 4n plus 2 electrons. So this will have very high Ka value, that means, and it will have lowest pK value. Okay, so B will have lowest pK value. Here if you see, if you remove proton again, it becomes anti-aromatic. So very clearly lowest pK will be B. Now the competition between A and C is there. So this is also anti-aromatic, but please understand, this is very strained ring, no flexibility at all. It is forced to be anti-aromatic, whereas here it is quite big molecule, so it is quite flexible. So you see, It's quite flexible and it goes like that, it becomes non-planar. It loses its planarity, so that this conjugation, so that this is not, see, this is not parallel to this p orbital. See, for conjugation all the orbitals have to be parallel to each other. So this p orbital is parallel, but this is not parallel, so it will not conjugate. So suddenly this conjugation is lost and becomes non-aromatic. So this will be little more acidic. That means you will have little lesser pK value than the first one. That means what we can say here is B will have highest pK, right? B will have highest pK, correct? And lowest pK C will have, because its Ka will be sorry, what am I saying? B will have lowest pKa. B will have lowest pKa. Sorry, here B will have lowest pKa, because if it has lowest pK value means it has highest Ka value, and A will have highest pKa, because that means the lowest Ka, because it will never lose proton, because system becomes anti-aromatic. This is non-aromatic. Still it is okay, but definitely anti-aromatic is not okay, right? Yeah, moving on to the next question. The HOMO of pi molecular orbital of methyl azide. So first we have to draw methyl azide. This is methyl azide. So basically there is a pi cloud here, there is a p orbital here, and there is a p orbital here, and of course other also there, but these two are interacting to forming this kind of system. So 3 p orbitals are there, so it will form 3 pi molecular orbitals. Now when it forms 3 pi molecular orbitals, we know psi 1, psi 2 and psi 3. Psi 1 will have 0 node, psi 1 will have 1, psi 2 will have 1 node, psi 3 will have 2 nodes. So when 0 node, that means plus, plus, plus. Whereas when it has to have 1 node, and it should look symmetrical also. So here there is no lobe at all, and this is plus and this is minus. I hope everybody understands this. I am talking about the sign on the p orbital, talking about a symmetry. So sorry, that is minus, I am so sorry. So yeah, so this is minus and this is minus and this is plus. So now and 2 nodes means this, you can see here plus is there, minus is there, plus, minus, and beside it again plus. So because sign changes, you are having one node, so you are having 2 nodes here. Now how many electrons are there? 3 p orbitals are there, 3 electrons are there. So 2 electron comes in psi 1, 1 electron come in psi 2, and no electrons is there in psi 3. So this is HOMO, highest occupied molecular orbital. So this is having this is occupied molecular orbital, this is also occupied molecular orbital, but this is having higher energy, so it is highest, and this is lowest unoccupied molecular orbital. So the answer is option number B, right? So that's it for this video. Thank you very much.